How we doing? Moving on with nuclear chemistry, we're going to discuss half-lives. This should be a review for most of you, or actually all of you, because everybody took earth science before chemistry. So just kind of think back to your earth science years. Half-lives are not bad. The hardest part about half-lives is being able to get the problem started, and we'll talk about strategies for that. All right. So this is going to be a bell ringer from the video that you had to watch on the most radioactive places on Earth. What unit is it measured in? All right, yeah, radiation is measured in sieverts. I believe in the video they did microsieverts and they equated it to bananas because bananas are radioactive because of the potassium that's in there. There's a natural amount of that. All right, but it's sieverts. If you didn't watch that video, I highly recommend you go back and watch it. Lots of actually, I think, cool information in there. I think most kids think as well too. All right, nuclear reactions versus normal chemical reactions. So last time I talked about this as well. All right, we're in a unit that's only dealing with the nucleus. We don't care about the electrons. This is the only time in chemistry that we don't care about electrons. So we're not talking about bonds. We're talking just about the things that go on inside the nucleus, what holds it together, how you can break it apart, and what happens when you do such things. All right, so they involve the nucleus, so they involve just the neutrons and the protons. All right. Generically speaking, what happens is nucleus opens up, protons and neutrons are rearranged, whether they're added or subtracted. They don't really disappear per se, but they are rearranged. To make nuclear reactions occur, though, you have to overcome the binding energy. Think of that as like the glue that holds the protons and neutrons together or holds the nucleus together. All right. You have to overcome that. And it's a tremendous amount of energy. And if you can break it apart, you can actually release that. And we'll talk about that in fission reactions later on in this unit. But normal chemical reactions involve only electrons, not anything that's involved in the nucleus. The nucleus is involved because of the positive charge. All right. But it's normally just a rearrangement of electrons that involves what we would call normal chemical reactions. All right, mass defect. We just kind of introduced this concept. You might, if you've taken physics, you might have heard of it. All right, but this is the one place that the law of conservation of matter does not get upheld. All right, mass defect means mass is defected or converted into energy. It's not a lot. It's not a lot of mass, but when that mass is converted into energy, it does, that little bit of mass does create a tremendous amount of energy. All right, so this is the one place that the law of conservation of matter is not upheld. All right, you probably have seen this reaction before, whether it's in some type of TV show or cartoon or someone's related to it before. E equals mc squared. All right, where E is the energy, M is this M is talking about mass, and then C is the speed of light, and then you square it. Speed of light, you're testing my knowledge, 3 times 10 to the 8th, something like that. I think I could be completely wrong on that. I forgot to look that up before. But you do get a lot of energy produced. This is the ability, you can see the background image and this whole unit is a mushroom cloud created by a nuclear explosion. That energy is tremendous, and that mushroom cloud is going to happen every time due to the physics of what's going on. I tell kids every year, if you want to make lots of money, try to figure out how to make cold fusion occur. Fusion is the joining of nuclei. All right, it's what powers the stars. The problem is if we could find a way to contain it and harness it here on Earth, all of our energy problems will be solved forever. All right, and we'll go into that later on. So here, just a quick review. Make sure you have your table O available to you. It's going to be very helpful for you. As you do these problems, you'll start to recognize what an alpha and beta and gammas are. So you won't have to refer to them, but just have it open for you. It makes life easier. Okay. So we're going to practice some more reactions here, determining the missing particle. So kind of like last time we did alpha emissions and beta emissions. Now we're going to take nuclear reactions and try to figure out what the missing particle is. All right, so here we have this reaction right here. So we got lead-210. So lead's atomic number is 82, whether they give it to you or not. All right, it's going to turn into something and then this particle right here. All right. If you refer to table O, this particle is a beta particle, but we'll talk about it. You don't need to know what that is right now. So what we need to know is what this missing particle is. So we got to figure out what the top number is and the bottom number is. So the top number, something plus 0 equals 210. So that's easy. The top number is 210. The bottom number, what plus a negative 1 equals 82? So that's going to be 83. So it's 210 over 83. Looking on your reference tables, element number 83 is symboled Bi, which is bismuth. All right, so you got 210 over 83 bismuth. So that's the completion, or that's the daughter nucleus, or completing this reaction. All right, like I said, I don't think they're super hard. You just have to add or subtract by up to 4, I think is the biggest number. Okay, so here we go. They give us the daughter nucleus in this one. They give us it turns into 214-84 polonium. But what they don't give us is what particle it gives off. There's usually some other particle that it gives off. So we have to do the math to figure out what it is. So what plus 214 equals 214? So the top number's got to be a 0. The bottom number, what plus 84 equals 83? So that's going to be a negative 1. So if you look on your table O of your reference table, 0, negative 1e, all right, that's your missing particle. All right, it's literally that simple. All right, it's just the math. And then where we get this letter from is what this bottom number is. All right, so here we've got 214 polonium. So you can see that we're kind of going down 214. Polonium is going to decay into something else. This is called a decay series. We're starting a decay series here. So our daughter nucleus in this case is a 210 over 82 lead. So what plus 2 equals, or what plus 82 equals 84? So that's a 2. The bottom number is going to be a 2. And what plus 210 equals 214? So the top number is going to be a 4. So 4 over 2 alpha, or 4 over 2 He. All right, so we have this missing particle. If you want to look up on table O what that missing particle is, I'm going to ask you in a little bit. So you have that. You should have table O right there for you. So that's our missing particle in this case. This is our daughter nucleus. All right, here we go. We got 206. Now we stopped the series, so we're just going to a different one. We got 206 over 81 TL. Produces this particle, which is beta particle, and then we got to figure out what the missing particle is. What plus 0 equals 206, so 206. And then negative 1 plus what equals 81, so it's going to be 82. So it's 206 over 82, which is lead. Okay, so we've got this one here. Now what I want you to do is go back each one of these reactions. I want you to label them as an alpha decay or beta decay. And we basically identify it based on what particles it produces. Okay, so go back, look here. This one produces, this is the daughter nucleus. This is our particle. So this particle, if we look on table O, that is a beta particle. So it's considered beta decay. We look at, this one's the daughter nucleus. This one's the particle we're looking at. It's the same particle as this one. So that's beta decay. And then we've got 4 over 2 He. You look on table O, 4 over 2 He is an alpha particle, so this is considered alpha decay. And then you've got 206 over 82 lead plus this particle right here, which is the same as the beta particle, so it's beta decay. Okay? All right, so now we're going to try some reactions on your own. So table N, determine the products. So here we go. So we got krypton turns into Rb, rubidium. All right, they have the same mass, so the mass of the missing particle here is going to be 0. All right, we need to look up krypton's atomic number, which in this case is 36. Okay, and now we have to figure out what number plus 37 equals 36. So 37 plus what equals 36? So 37 plus a negative 1 equals 36. And then the top number is 0, so negative 1 over 0, or 0 over negative 1. I said that flip-flopped. This particle is a beta particle, so this is considered beta decay. Do the next one. All right, so we got the same thing. They give us a parent nucleus, TH232. You're going to need to look up the atomic number of TH. TH's atomic number is 90. All right, and then we want to know what the missing particle is when this is the daughter nucleus. So what plus 228 equals 232? So that's going to be a 4. And what plus 88 equals 90? So that's going to be a 2. So it's going to be 4 over 2 He. All right, this 4 over 2 He is an alpha particle, which means it's alpha decay. Okay? All right, now transitioning to half-life. So that was kind of wrap up of last class, just kind of reviewing it again. So half-life, I approach half-lives as a very logical progression. Some people struggle with the logic behind it, but you have to, if you don't, then if you do struggle with it, play this video again. Make sure you take good notes on this. All right, half-life is the time it takes for half of a sample to decompose. Remember, radioactive isotopes are unstable because they have a non-one-to-one ratio of protons to neutrons. All right, and when they are unstable, they will decompose in a pretty specific amount of time. All right, the rate of transformation depends only on the reactant. All right, doesn't matter how much you have of it. It doesn't matter the pressure, the temperature, anything. Nothing else can affect half-life. The only thing that impacts the half-life or how fast it's going to occur or how slow it's going to occur is what the actual substance is that is decaying. All right, you can't speed it up or slow it down unless you're Dr. Strange and you can change time. Okay, so kinetics of radioactive decay. So this thing down here is a Geiger counter. All right, I'm trying to think where you would have heard it, but you hear like the click, 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 click. The more radioactive it is, the faster the clicks are. The less radioactive it is, the slower the clicks are. You'll definitely see it in the video. The most dangerous radioactive places on Earth. All right, that's an old school one. They had a digital one in that one. So what happens for each duration or each half-life, one half of the substance decomposes. All right, for example, you got radium-234 has a half-life of 3.6 days. Okay, if you start with 50 grams of radium-234, how much are you going to have left after 3.6 days? All right, you're going to have exactly half of 50 grams. What's half of 50 grams? Half of 50 grams is 25 grams. So now after a second half-life, which for radium-234 would be 7.2 total days or another 3.6 days, whatever you want to say. All right, you're going to have half of the 25 grams left. So half of 25 grams is 12.5 grams. So you can go another time frame for half-life period. So you're going to add 3.6 to 7.2, so you get 10.8. So after a total of 10.8 days or 3.6 days from the 7.2, you're going to have half of 12.5 grams. Half of 12.5 grams is 6.25 grams. All right, you can go another half-life, and you can keep doing this. All right, you can add 3.8 days to 10.8, all right, which, or 3.6, sorry. Whoa, 14.4, I believe, is the days, and you half of 6.25 is 3, oops, I didn't go that far. Half of 6.25 is 3.125 if you wanted to keep going. And you can keep going. You can do this mathematically. You can set a proportion and figure it out. But that's really the hardest type of problem you're going to get in this. It's just thinking of it that way, and I call it logic. All right, this one asks for a fraction of a sample of strontium-90 will remain after 175 years. Okay, so this is where I want to introduce you guys to table N on your reference tables. All right, table N gives the half-life time and the decay mode for the isotopes that we need to be familiar with. They are organized alpha based on their symbol, not by their name, if that makes sense. Okay, so get the half-life from table N. So you look on table N, the half-life of strontium-90. You find it is strontium-90 is right there, is 29.1 years. All right, determine how many half-lives elapse in the time period. Okay, so this is usually step one of any problem. Figure out how many half-life periods there are, and it's different depending on the problem. This is where you got to kind of understand what's going on. It's what I call logic. In this case, you're going to take your total time, which is 175 years, and you're going to divide it by the time for one half-life. All right, so the number of half-lives is the time elapsed divided by the half-life period. I don't like using this formula. I put it up here because I believe you use it in earth science. This is probably the only time I'm going to use it. All right, but the number of half-lives in this case is going to be 175 divided by 29.1. Right, when you do that, you get some number really close to 6.01 half-lives. So that means we're going to have 6 half-life periods. So they want to know what fraction remains after 6 half-lives. So now it's the easiest way I think it is to do this is just to get a piece of scrap paper and just start writing it down. So if they want to know fraction, a whole fraction, starting off with a whole sample is just 1 or 1 over 1. After one half-life, you're going to have half of that remaining, correct? And then what we do to count how many half-lives is we count the arrows. So that's 1. After another half-life, we're going to have half of that remaining. After another half-life, half of that. And we keep going, and we have to stop at 6 because it says 6 half-lives. Okay, so this is 6 half-lives. Now, what's the total fraction remaining? So now you have to multiply a half times 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 1. So we don't really have to worry about the 1 because it's going to be itself. So 1/2 times 1/2 is 1/4. 1/2 times 1/2 is 1/4. 1/2 times 1/2 is 1/4. So we get 3 1/4s. 1/4 times 1/4 is 1/16. And then 1/16 times 1/4 is 1/64. All right, because it asks for a fraction, we have to leave it in this. All right, if they asked us if you had 80 grams to start with, how much would remain? So instead of starting with 1 here, we would put 80 grams here. And then it would go to 40, and then to 20, and then to 10, and then to 5, then to 2.5, then to 1.25. Okay, so the process is the same. It's just your starting point is, instead of being a 1, is whatever grams they give you. Okay? So if a sample of strontium-90 has an original mass of 52 grams, what mass will remain after 175 years? So this is kind of like the problem I was talking about last time. So I kept the isotope the same, strontium-90. All right, 175 years is just like we did over here. 175 years divided by 29.1 is 6 half-lives. So in this case, instead of starting off with 1, we're starting off with 52 grams. So 52 grams, and we have to divide it in half 6 times because in 175 years, there'll be 6 half-life periods. So 52 divided in half is 26. And that's 1 half-life. Count the arrows. 26 divided in half is 13. 2 half-lives. 13 divided in half is 6.5. 3 half-lives. 6.5 divided in half is 3.25. That's 4 half-lives. 3.25 divided in half, let's see, that's 1.625 or something like that. Yep, 1.63. So that's 5 half-lives, and then 1.63 dividing in half is 1.3 something. Oh, sorry, not 1.3. 0.8, I don't know why I saw the 3 there. 0.815 grams. So after 175 years, you would have 8.15 grams. Now this is important because if it's something that we have to store for a long time, it takes 175 years to get to some amount under or less than a gram. All right, okay. And then this is a different way. Some people mathematically approach this. 50, you figure out the fraction, you go through 2 times 1/64, and you get the same number. I don't worry about that one too much. All right, we are done for the day on this. You're gonna need to practice your half-life work.